Chemical bonding 4. Covalent bonding and covalent structures. Bond and molecular polarity. The essential idea here is the covalent compounds formed by the sharing of electrons, and the Lewis structures show the electron domains in the valence shell and are used to predict molecular shapes. For the nature of science, we're going to think again about how scientists use models as representations of the real world. So, we've already looked at non-polar versus polar covalent bonds. The equal sharing of electron pairs between two atoms results in a non-polar or pure covalent bond. The difference in the electronegativity of the two atoms must be under 0.3. Are equally distributed between the two atoms. You can see here this electron pair directed between the two chlorine atoms. Polar covalent bonds. These have an unequal sharing of electron pairs between two atoms. If the electronegativity difference is between 0.3 and 1.7, which it is in this case over here, we've got an electronegativity difference of 1, then the electrons shift to the atom with the high electronegativity. So instead of the bonding electrons being here, the bonding electrons will be further towards the chlorine. And then of course bond dipoles form. The dipole will be heading this way up, and you'd get delta negative over here, delta positive there. But we also have non-polar versus polar covalent molecules. Non-polar covalent molecules. The electrons are equally distributed around the molecule, and there's no dipoles present on the molecule. For polar covalent molecules, there's electrons are unequally distributed around the molecule, and the dipoles are present on the molecule. So, for non-polar covalent molecules, no permanent partial charges are on the molecule. You can see this is perfectly symmetrical. The electron cloud is perfectly symmetrical, but there are partial charges on the molecule. You can see the electron cloud is larger over the red atom, which I guess in this case we call oxygen. And so you have a negative dipole here and a positive dipole over here. You can test for polarity, the electric field test. Polar covalent molecules are, I guess, a bit like tiny magnets, okay? And water is a polar covalent molecule. If I was to draw water here, like so, this side of it is delta positive, and this side is negative. And if you've got a big balloon like this, and someone's rubbed the balloon, you're either going to get a positive charge on the balloon or a negative charge, depending if electrons were added or removed during the charging process. Let's say electrons were removed, you'd have a whole bunch of positive charges here. Okay, if this is the case, then the delta negative, the negative dipole on the oxygen, would be attracted to it, and you get a bending of water here. With non-polar covalent molecules, there's no dipole, there's no charge on the molecules, and so you wouldn't get a bending of water. The water would instead go straight down the sink. For another look at the electric field test, please go to molecular polarity, the FET activity here. Okay, press pause, have a go at that, then come back. Right, another look at the electric field test. With polar molecules, if you place them between electric plates with a negative charge and a positive charge, then when there's no electricity passing, the molecules will just be randomly aligned. If you turn the electricity on, then this plate here becomes negatively charged, and this one here becomes positively charged, you see that the molecules will move and align themselves in the electric field, with the negative side of the molecule facing towards the positive side facing towards the negative. With non-polar molecules, this of course won't happen. Even when you turn the electricity on and this plate here becomes charged negatively and this is positive, there's no charge on the molecules, so they won't rotate to align. To deduce the polarity of a molecule, two atom molecules, fairly straightforward. Non-polar covalent bonds have an electronegativity difference of below 0.3. Okay? So there's no areas of partial charge. There's no dipoles formed on the molecule. With polar covalent bonds, when there's a difference in electronegativity between the two atoms of between 0.3 and 1.7, then we get a polar covalent molecule. And you can see here, the bond dipole goes from the hydrogen to the chlorine atom, as we know, and we can use this little green arrow, okay? But this will also set up, since these are the only two atoms in the molecule, it'll set up a dipole moment on the molecule itself. And this is shown here with the violet molecule there. It shows the dipole moment of the molecule. Areas of partial charge, or the dipoles, form on the molecule. There's a cloud of electrons. Sorry, let me put it a better way. There's a greater chance of finding electrons over this side than there is this side. So the dipole, positive dipole, is next to the hydrogen, and the negative dipole is on the side of the chlorine. You've also seen this PhET simulation, and it's a fantastic way of looking at it, I think, because you can see here with a non-polar molecule, we've got atom A, and we've got atom B, and we've got the electron cloud around here, and it's shaded in evenly. It's uniform grey. But now look at the polar molecule. You can see there's a lighter shading over here, darker shading over here, and this is just signifying that there's a greater chance of finding electrons over here. The negative dipole is over here, and you can signify that with one of our arrows. The atom B has a greater electronegativity than atom A. Here, there's an equal electron distribution here, and so no dipoles form, sorry. And here we have an unequal electron distribution, so dipoles do form. What if we have 3 atoms in a molecule? Some non-polar molecules have polar covalent bonds. Okay, let's look at carbon dioxide. The carbon oxygen is a polar covalent bond because the oxygen is more electronegative, and there's 2 of them in here, and we have a linear shape, but the bond dipoles cancel out. You can see they're pointing in identical opposite directions and the same size, so there's no overall dipole moment, so it's a non-polar covalent molecule. Okay, so it has polar covalent bonds, but overall it's a non-polar covalent molecule. There's no dipoles or partial charges. On your PhET simulation that you used earlier, if you were to make carbon dioxide there, you've got carbon in the middle, 2 oxygens. You see the carbon, we have just set it in the middle, and we've got the oxygen here and here with high electronegativity. You see it's not aligning itself between the charged plates. Okay, let's have another look. Let's look at water. Polar molecules usually have polar covalent bonds, and they must not be symmetrical. So we've got polar covalent bonds because the oxygen is more electronegative than the hydrogen, 2 of them. There's a bent angular shape to the molecule. The bond dipoles are reinforced, they're both pointing the same way. So there is an overall dipole moment, and it's heading in this direction, following the direction of the 2 bond dipoles, which sum together to make an overall dipole moment in the molecule. So we get a polar covalent molecule. And dipoles, partial charges, form on the molecule. And you see this side here, where the hydrogens are, will be the positive dipole. And over here, where the oxygen is, will be the negative dipole. Of course, this is because it is non-symmetrical. If we're to make this on our PhET simulation, we've got the oxygen here and the two hydrogens. The oxygen is fairly electronegative, hydrogens not so much so, but they're the same, you see. Charge plates, and it will line up so that the oxygen is pointing towards the positively charged plate because the molecular dipole is facing that way. Okay, some polar molecules have non-polar covalent bonds, but they must not be symmetrical. So we've got non-polar covalent bonds in this, obviously, because they're all oxygen, so they all have the same electronegativity. It's a bent angular shape, so it's not symmetrical. The lone electron pairs on the central oxygen atom here, and as an overall dipole moment forms, okay, and it's facing this way. Down here we've got 1, 2 lone pairs here, 1, 2, 3 lone pairs up here, just 1. So an overall dipole moment forms facing down towards where there are more lone electron pairs. And so we get a polar covalent molecule even though the bonds themselves are not, do not have dipoles. And so dipoles, partial charges, do form on the molecule. And the delta positive will be where there's only one lone pair. And the delta negatives occur down this end where there are more lone pairs. Of course, it has to be non-symmetrical for this to occur. Okay, the role of symmetry in molecular polarity. We're going to deduce the polarity of a molecule. If a small molecule is non-symmetrical, bond dipoles do not cancel, and the molecule is polar. Let's have a look at this. We've got a symmetrical arrangement here. I've just drawn carbon dioxide. We've got bond dipoles, both facing away of an equal magnitude, and so these bond dipoles cancel. Therefore, there's no net dipole moment. Therefore, there's no dipoles on the molecule, and so it's a non-polar molecule. Conversely, a non-symmetrical arrangement such as water, the bond dipoles add up, they're facing in the same direction. And there is therefore a net dipole moment which forms. The dipoles form on the molecule. We've got a negative dipole up at the oxygen side and positive dipoles down by the hydrogens. And so we end up with a polar molecule. Okay, 3 atom molecules. It's your turn. See if you can work out if these are polar molecules or not. Press pause and have a go. Okay, so the hydrogen-carbon bond is has a dipole and it's facing towards the carbon, which is more electronegative than the hydrogen. And we've also got a polar covalent bond here between the carbon and the nitrogen. Nitrogen is more electronegative. So they're both facing the same direction, and so we get a polar molecule. The delta positive will be on the hydrogen side, and the delta negative, or the negative dipoles, sorry, will be on the nitrogen side. Here, for sulfur dichloride, we've got sulfur chlorine bonds, which have which are polar covalent bonds, because the chlorine is more electronegative than the sulfur. And we've got polar covalent bonds here again for the same reason. They're facing in the same direction. It's non-symmetrical, and so we have a dipole moment on the molecule. It's a polar molecule. The positive dipole will be where the sulfur is, and the negative dipoles down by the chlorine atoms. Okay, what if we've got 4 atom molecules? Have a go at this, please. Press pause. I know if you haven't pressed pause, press pause. Good. Okay, well, we've got polar covalent bonds here, here, and here. And it is symmetrical, isn't it? And so we've got a trigonal planar, and all bonds are the same. All bond dipoles are the same, sorry. And so symmetrical molecules, therefore bond dipoles cancel out. We've got a non-polar molecule. What about here? Well, we've got bond difference of 0.8. So we've got polar covalent bonds. And, sorry about that. They are all pointing towards the nitrogen. They're all pointing in the same direction. It's a trigonal pyramidal. It's a non-symmetrical molecule. Therefore, the bond dipoles are adding up, and there's a net dipole moment. So we have a polar molecule. The negative dipole will be up by the nitrogen, and the positive dipoles by the hydrogen atoms. Can you have a go at this one, please? First pause. Pause. Okay. You've got a polar covalent bond between the carbon and the oxygen, because the oxygen is more electronegative. And you've got smaller polar covalent bonds towards the carbon. And you see it's only a difference of 0.4, but that's enough. Remember, it's got to be above 0.3. So, trigonal planar. Bond dipoles are different, and it's a non-symmetrical molecule. The bond dipoles are adding up, they're all facing in the same direction. So therefore, there is a net dipole moment, and we have a polar molecule. The positive dipoles will be on the hydrogen atoms, and the negative dipole by the oxygen. Oh, so we've got 5 atoms here. This is so much fun. So we have polar covalent bonds here, 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 and here. The small difference, 0.4, but that's sufficient. And the dipoles, the bond dipoles, are all pointing towards the carbon. It's tetrahedral. All bond dipoles are the same, and it's a symmetrical molecule. Therefore, the bond dipoles cancel each other out, and it's a non-polar molecule. What do we have? We've got a fluorine atom up here, carbon, 3 hydrogens, and so we're going to get a polar covalent bond here, because there's quite a large electronegativity difference between the fluorine and the carbon, and then 3 polar covalent bonds here with the smaller electronegativity difference. It's tetrahedral. The bond dipoles are different. It's a non-symmetrical molecule. The bond dipoles add up to give a net dipole moment. You can see it facing towards, pointing towards the fluorine. And so it's a polar molecule. And we're going to get the positive dipoles down here where the hydrogens are, and the negative dipole up where the electronegative fluorine atom resides. Okay, try out some of the other examples on the FET. Please go and do that now. Do it. Do it now. Okay, goodbye.